All right, welcome to lesson 6 of hazardous material operations. Tonight we're going to talk about chemical monitoring and personal protective equipment. Monitoring. Sometimes hazardous materials releases are not always apparent. That's one reason why we do monitoring. So what is monitoring? It is the characterization of an atmosphere utilizing instrumentation. It helps determine the presence and concentration of a hazardous material. Now, notice it says helps to determine. There are no guarantees when it comes to hazmat monitoring. Let's talk about some general monitoring characteristics. What does it help us do? It helps establish hazard control zones, identify unknown products, assess isolation and evacuation zones, identify risks to human health, helps identify the PPE we're going to use, helps identify mitigation options, and helps assess environmental hazards. It also helps us know when our decontamination process is complete. Keep in mind, no one device, no single device can detect, identify, or measure all hazardous materials. There is no one size fits all. There's no one device that will monitor everything. All devices also have their own strengths and limitations. We have to understand those strengths and limitations in order to understand the information our monitoring devices provide. So we have to be able to interpret what they say, what information they give us in order to make decisions. So what are some characteristics of monitoring devices? When they're electronic devices, they need to be certified as intrinsically safe, which means they are not going to create a spark, which could cause a fire in a flammable atmosphere. They also should be listed by UL, FM, or NEC. Also, they should not be subjected to any aftermarket alterations. You don't add anything or take anything away from the monitor that the manufacturer doesn't approve. So what are some features of monitoring devices? We're going to talk about reliability, sensitivity, cross-sensitivity. There's detection limits, selectivity, portability, accuracy, data logging capability, operating limits, ease of operation, response time, calibration, and relative response. We're going to talk about a few of these. So what is sensitivity? Sensitivity describes the lowest concentration of a material that the device will detect. Anything below that, and the device is not going to register. For example, methyl mercaptan, the odorant that's put in methane, our olfactory sense, our sense of smell, can detect that at much lower concentrations than a combustible gas monitor. That's sensitivity. Selectivity. That's how well a device will differentiate between chemicals. Sometimes we find ourselves in an atmosphere or a situation where we have multiple chemicals present. How well can the monitor differentiate between the different chemicals? That's its selectivity. Something with high selectivity is going to be able to differentiate. Something with low selectivity is not. Calibration. What is that? It's adjusting an instrument, a monitoring device, to correspond with a known concentration of a material. So when we take a monitoring device and we put it in calibration mode, we are then going to expose that sensor in that device to a known concentration, and we're going to tell that monitor, this is the known concentration. That way it knows the signal it's getting from the sensor is that concentration. And now it can judge any concentration within its sensitivity range accurately. How often do you calibrate? That's per the manufacturer. Usually that's monthly. Some environmental factors come into play with calibration. They are location. So for us in emergency response, you don't want to calibrate a monitor in a dirty or dusty environment or right next to your vehicle exhaust with it running. There's temperature can affect the calibration, air temperature, also the monitor temperature, the gas temperature, and the humidity. When you calibrate, you need to know what the manufacturer of the monitor specifies for the temperature and the humidity ranges. Cross sensitivity. Some chemical specific sensors will respond to multiple chemicals. An example of that is some carbon monoxide sensors also respond to hydrogen gas. So, in an environment where both gases are or may be present, the monitor readings are not accurate. You need to use other means of detection. One possibility we'll talk about later is the colorimetric tubes. So, for example, real world example, warehouses that use battery powered forklifts. The batteries they use are lead acid batteries. When they're charging, they emit hydrogen gas. Many times, these warehouses, the heating system is powered by natural gas. So you have the possibility of carbon monoxide being present if there's a problem with the heating system. And if they're charging batteries, you also have hydrogen gas present. If you're at a location such as this with both a source of carbon monoxide and a source of hydrogen gas, and you're looking with your standard 4-gas monitor for carbon monoxide, you need to ask, are you charging any batteries? If they are, if you're getting any readings for the carbon monoxide sensor, those readings cannot be trusted. Same thing with a residence. Many times people will charge batteries for cars, for boats, lawnmowers, golf carts. They'll charge them maybe in their garage. Sometimes, if they don't have good weather sealing between the garage and the house, that hydrogen gas can build up and make its way into the house. Anytime you are looking for carbon monoxide and there is a possibility of batteries being charged, you need to ask and eliminate that source of hydrogen gas before you can determine whether your readings for carbon monoxide are accurate. Like I mentioned earlier, the monitor just tells us a number. We have to take that information and our knowledge and our experience to analyze that information. Relative response. This is the difference between the response to a calibrated chemical and to a chemical to which the instrument is not calibrated. Here's an example. Your LEL, or the combustible gas sensor. Normally, many times, that sensor is calibrated to methane. If you were searching for propane, then your monitor's readings will not be accurate. Many times, manufacturers will provide a chart of conversion factors. You apply the conversion factor to the monitor readings to determine the true reading. So, for example, your combustible gas monitor is reading 7. That's for methane, and you're looking for a propane. The correction factor, let's just say, is 1.6. Let's do some math. Take 7, multiply it by 1.6. The actual reading is 11.2, which is above 10% of the lower explosive limit. That means we're getting closer to the lower explosive limit. All right, when we go into monitoring an incident, we get called to an incident, and as soon as we recognize or suspect that this incident is a hazardous materials incident, there are some priorities in order in which we want to monitor. So the order of these priorities is critical. The first thing we're going to monitor for is radioactivity. Second, corrosive vapors. Third, oxygen levels. Fourth, combustibility. And fifth, toxicity. Why this order? Very good question. In general, we're going to monitor in the order in which something could get us furthest and we have the least protection from. So radioactivity. So we talked about before, the most common types of radiation that we may encounter is alpha particles, beta particles, and gamma rays. Remember, alpha particles can be blocked by your clothing and do not travel very far. So we're not really looking in this case for alpha particles. Beta particles can travel several feet, 10, 30 feet, depending on the energy. However, they can go through our clothes and through our skin. We need some metal. Some metal, aluminum will block beta particles. Gamma rays travel the furthest, the most energetic, and are difficult to block. They're the ones that can get us the farthest away, and therefore, and then we have the least amount of protection from. So we want to monitor for that first. Secondly, corrosive vapors. Corrosive vapors, we monitor for that next because we're going to be using equipment, and some of that equipment is very sensitive and relatively delicate, and it contains metal parts. Corrosive vapors negatively affect metal. If we take our several $100 4-gas monitor into a corrosive vapor atmosphere, we are increasing the likelihood that we're going to destroy that monitor. So not only is it going to cost us to replace, but now we don't have a way of monitoring for the gases that it was designed to monitor. So we're going to monitor for corrosive vapor second to protect our monitors for the most part. And if we're going to be wearing SCBA, we also don't want to be exposing the metal components of our SCBA to the corrosive vapors. Thirdly, oxygen levels. We want to measure oxygen levels next. We want to make sure because we want to make sure that there is enough oxygen concentration present in the air in order to accurately monitor for combustibility. The way combustibility sensors work is they actually burn, and they burn the combustible gas. And if there's a combustible gas present, it increases the electrical signal. If there is, and they are assuming that there is a normal concentration of oxygen. If there is less oxygen in the air, then it's not going to burn as bright and going to give us a false low reading. If we have higher than normal oxygen levels, then it's going to burn stronger and give us a higher than actual reading. Combustibility can get us next, distance-wise, and then toxicity. I'm going to measure for toxicity last. So that's why we order the monitor in this order. So let's take each one in turn. Radiation, types of monitor, the old standby, the Geiger counter. Geiger counters can, with different attachments, detect alpha, beta, and gamma radiation. Some have an analog dial like this one, where you have to turn that knob to change the scale. So you have to really pay attention to what scale you're on. Other ones, newer ones, have a digital readout that may be auto scaling, a little easier to use. Then there's also personal dosimeters. These can measure both the real-time rate of radiation and calculate how much radiation you've received. This particular model detects gamma radiation. How do we check for corrosivity? While there are chemical specific monitors that are also corrosive, most hazmat teams and emergency response organizations don't utilize them. Where you would see them is in industry emergency response, because they already know that chlorine is present. So it makes it worthwhile. They have chlorine on site, so they make it worthwhile that they would have that specific monitor. For emergency response, we pretty much rely on pH paper. You can use it dry or wet, just wet with water and held in the air. And what you're looking for is a change in color. So the base color of the paper is somewhat orange. And then as you can see there, the scale, it's in whole numbers. So again, we're not dealing with scientific laboratory grade equipment. We're looking for generalities, whether something's going to be a alkaline or basic or acidic atmosphere. If you wet the paper and put it in the atmosphere, it's going to react a little bit faster and at lower concentrations. Third, we're going to monitor for oxygen. So the sensor inside measures a chemical reaction, which creates an electrical output proportional to the oxygen level. So the more oxygen, the more reaction, therefore the more chemical or electrical output, higher numbers. These are also temperature dependent. If your ambient temperature is outside its operating range, then your readings are not going to be accurate. So when monitoring for oxygen, normal air contains, now this says 20.9% oxygen. So most of the time you're going to see in general 21% oxygen. Practically, when almost every oxygen monitor I've ever used has registered 20.9. So think of 20.9 and 21% oxygen to be the same for our purposes. Anything less than 19.5% oxygen is considered oxygen deficient. Therefore, as I mentioned before, your LEL readings will not be accurate. That's why we have to monitor for oxygen first. We have to make sure there is enough oxygen in the right concentration for our LEL sensor to be accurate. On the other end, greater than 23.5% oxygen is called oxygen enriched. Also, your LEL readings will not be accurate. Most oxygen sensors only last 1 to 2 years. So you're going to be changing them out and they can get relatively expensive. If you're monitoring in an environment that contains a chemical with additional oxygen in their molecular structure, this can cause that sensor reaction to quote, burn brighter and shorten the sensor life. Your monitor should tell you when to replace the sensor. But just keep in mind that you're going to shorten the sensor life if you're using it in an environment with a chemical with additional oxygen. The optimal temperature for most oxygen sensors is between 32 degrees and 120 degrees Fahrenheit. Check your manufacturer operating limits for specifics. Next, we monitor for combustibilities. They use a process called catalytic oxidation. How's this work? When a combustible gas contacts a platinum-coated coil of wire inside the sensor, it oxidizes, and the wiring resistance is increased by the increase in heat. The measured increase in resistance is proportional to the percentage of combustible gas. So we have to have oxygen in order for it to oxidize and get that measured increase in resistance in that wire. On the left is what a common 4-gas monitor looks like. This one in particular monitors for LEL, oxygen, carbon monoxide, and hydrogen sulfide. On the right is a single combustible gas detector. Here's another example of a 4-gas monitor and a chart with common flammability ranges. So with methane, the lower explosive limit is 5% in air, and the upper explosive limit is 15%. As we talked about chemical and physical properties, with the LEL and the UEL, if your atmosphere falls outside 5% and 15%, and methane's the only chemical present, then you should not have a flammable atmosphere. As you know, as propane is just under half of methane's lower explosive limit. And got a couple more there. If you notice, carbon monoxide is flammable in a very wide range, 12.5% to 74%. Then take a look at the next one, ethylene oxide. It has one of the widest flammability ranges, 3% in air to 100% ethylene oxide is flammable. So what does the LEL, or combustible gas monitor, tell us? The reading shows the percent of the lower explosive limit of the selected gas. So the reading equals the LEL of the calibrated gas divided by 100. So it's percent of LEL. Cent is 100, LEL per 100. So for example, most 4-gas monitors are calibrated to methane. As we saw in the previous chart, the LEL of methane is 5%. If your monitoring is displaying or reading 5, then the concentration of methane in the air is 5% of the lower explosive limit, which is 5%. You take 5% of 5%, that is 0.25% concentration of methane in air. So you are at 0.25% of a concentration, methane concentration in air. So you're good to go. You can change this, but in standard practice is for the LEL sensor, it will alarm at 10% of the LEL. So once that reading gets to 10, it will alarm. So 10 or higher, it will alarm. Okay? That means you still have 90% of the LEL to either reduce the concentration in air or get out of that environment. Okay? So when it alarms, if it alarms at 10% and it stays at 10% and doesn't get any higher, you are not in a combustible or flammable atmosphere. That alarm at 10% gives us a safety factor to either make the situation better or move, get out of that atmosphere. So when the meter is detecting a combustible environment, when it reads what concentration? So what will your monitor read if you are in a combustible atmosphere? 100%. Because remember, the LEL reading is the percent of LEL. So if we have to get to a 100% of the LEL in order to be in a flammable atmosphere. When we looking at chemical specific monitoring, they usually use an electrochemical cell. It's typically used in the 4-gas with a pump. They are 90% accurate in 30 seconds, 100% accurate in 2 minutes. Many of the ones that I have experienced have a countdown. Once you've turned on the monitor, it will tell you, it will count down in so many seconds when it's ready. Those sensors have to get warmed up before they will be accurate. So in most modern 4-gas monitors, it will tell you when it's ready. But in general, they're not going to be 100% accurate till at least 2 minutes. If your monitor happens to not have that countdown, then use this in general. Sometimes the atmosphere we need to monitor is not close by. So speaking specifically of a confined space. We don't want to enter a confined space until we have characterized the atmosphere in that confined space. How do we do that? We can use tubing. If your monitor has a pump. If your monitor does not have a pump, then you cannot add tubing because there's nothing to draw the air through the tubing. In general, you're going to add 2 seconds for every foot of tubing you add, unless otherwise noted by the manufacturer. So for example, if you're using 10 feet of tubing, you need to let it sample for at least 20 seconds before taking the readings. So you take every foot, multiply it by 2, and that's how long you need to sample before you take a reading. So don't move the monitor around or change locations until you've got that accurate reading. When it comes to toxicity, they're available for a variety of gases. You can get specific ones for carbon monoxide, hydrogen sulfide, chlorine, ammonia, sulfur dioxide, hydrogen chloride, hydrogen cyanide, and nitrogen dioxide. So many times in industries, fixed facilities, they'll have specific monitors for the chemicals that they know they deal with. What are some types of toxicity monitors? On the left is a photo ionizing detector, or a PID. So in that example, in that picture, that's a standalone PID. Sometimes you can get 4-gas monitors that have a PID built in. They'll call that the VOC, will be the label. You can also use colorimetric tubes, which there's an example on the right. Let's talk about the photo ionizing detector, or the PID. They can detect a wide variety of gases in small amounts. Keep in mind, they will not indicate what materials are present, only the concentration that they detect. So it doesn't tell you what it's detecting, it only tells you how much. It can help identify potential areas of concern and possible leaks or contamination. And they have sensitivity from 0.1 to 2,000 parts per million. Those are the most common. However, you can get units that measure in parts per billion. And as we learn from our hazard and harm unit, the smaller the unit, the more toxic the chemical is. So how does it work? It uses an ultraviolet lamp to ionize contaminants in the air. When those contaminant particles become ionized, they carry an electric charge, which can be read by a sensor. The more contaminants, the higher the electrical charge, the higher the reading. Keep in mind that this measures gases or vapors, and that whatever gas is you're looking for, they only detect chemicals that have a property called ionization potential. If a chemical does not have an ionization potential property, then the PID cannot detect it. Also, the PID can only detect materials whose ionization potential, its IP, is less than that of the UV lamp. The standard lamp is 10.6, So any chemical that you're wanting to detect has to have an ionization potential less than 10.6. Sorry about the spelling mistake. I'll fix it. So here's a chart with some examples of gases and charting their ionization potential. So on the left, we start at 0 in the ionization potential, and then we move to the right, you can see the line where the 10.6 is. All the 1, 2, 3, 4, 5, top 5 chemicals there will not be detected by a PID with a lamp of 10.6. It just won't see them. It's as if they're not there. So you're not going to monitor with a PID for carbon monoxide, oxygen, carbon tetrachloride, methylene chloride, or acetic acid. So if you're trying to find the concentration of a chemical in the atmosphere, you have to know its ionization potential. First of all, does it have one? And secondly, is it less than 10.6? Also keep in mind that you can have a mixture of gases. Which one is it detecting? If they both have an ionization potential less than 10.6, it doesn't know. You would have to know a lot more science to figure that out. More than what this class deals with. So what can a PID measure? There's a whole lot of restrictions on what a PID can measure. So how is it useful for us? It can measure some organics, some aromatics such as benzene, ethylbenzene, toluene, and xylene. Just used it to monitor for xylene a couple of weeks ago. Works great. Can also monitor ketones and aldehydes such as acetone, methyl ethyl ketone, MEK, acetaldehyde, also amines and amides, chlorinated hydrocarbons, sulfur compounds. Hold on, let's go back for a second. Notice it says mercaptans. It's not on there. I was hoping that methane would be on there. Mercaptans, carbon disulfide, but not carbon monoxide. Unsaturated hydrocarbons, butadiene, isobutylene. Most PIDs are calibrated to isobutylene. Alcohols such as ethanol can be measured, saturated hydrocarbons, butane and octane, and then some inorganics such as ammonia and arsine. So what can it not measure? Just as important, radiation. PIDs don't measure radiation. They don't measure the standard air components such as nitrogen, oxygen, carbon monoxide, or water vapor. It also doesn't detect other toxics such as carbon monoxide or hydrogen cyanide or sulfur dioxide. It does not measure, here we go, natural gases such as methane and ethane. So ethane and ethanol, relatively similar. One can be measured by a PID, one cannot. Acids, don't use a PID. Freon or ozone, don't use a PID. So some problems with PIDs. The lamps are affected by dirt and dust, and they do require some cleaning, some maintenance. Higher levels of methane may suppress some readings. So even though it cannot detect accurately methane, high levels of methane may suppress some readings. So in the presence of methane and something else, can't be trusted. And extreme humidity plays a role in the reading as well. Colorimetric sampling tubes, colorimetric sampling types. You have single tubes. So the example there is a Draeger tube with a Draeger hand pump. There's multi-tube systems and then also chip measurement systems. I've only have experience with the single tubes and the multiple tube systems. How do they work? The tubes, the glass tubes are filled with a reagent material which changes color when exposed to the intended gas. You break off the tips, the two ends of the glass tube, and the air sample is drawn across the tube in a specific quantity. So each tube will have a number on it that corresponds to the number of, we'll go back one, pumps that you squeeze that hand pump with, and you'll see that there's a counter on it as well. So it will count how many pumps you've done. The tube changes color in the presence of the contaminant that the tube is intended to detect. So we talked about our example earlier at the warehouse where batteries are being charged, and we're also looking for carbon monoxide. Excuse me. So we're trying to monitor for carbon monoxide with a carbon monoxide sensor, but we also know that hydrogen gas may be present. What do? We can use a carbon monoxide specific colorimetric tube. It uses a different process to detect the carbon monoxide. We can use that colorimetric tube and get a more accurate concentration reading. So before you monitor, what do you need to do? Besides learn all about your monitor and how to use it, you need to do some pre-monitoring checks. So you get called to an incident, this is what you do in step. Battery check. Make sure your battery's working. Make sure it's been calibrated. Should be doing that regularly per the manufacturer's recommendation. Perform a bump test. What's a bump test? A bump test is when you expose, it's very similar to calibration. The procedure is very similar to calibration, but you expose the monitor to your calibration gas and make sure that it will alarm at the readings that you expect it to alarm. You're just checking it to make sure that it's going to alarm when you need it to. That's a bump test. Also, you want to ensure all attachments are in proper working order. Many times, a monitor will have a replaceable filter to protect it. Make sure that that's in place and not contaminated. Otherwise, you need to replace it. There are two stages of monitoring. There's recon monitoring and there's operational monitoring. Recon monitoring, it determines if a hazard is present. Sometimes we get called, we take out our monitors, and we don't pick anything up. We want to make sure that it's present. Also, recon monitoring is going to help us determine our initial control zones. We need to know where the hazard is so we can know how to keep people out of it and where it's going. Recon monitoring, getting information about the scene, layout of the scene. Then there's operational monitoring. 29 CFR 1910-120, remember that's HAZWOPER, says we shall identify 4 things. These are important to remember. Radioactivity, we have to monitor for radioactivity. We have to monitor for an ideal H condition that's immediately dangerous to life and health. We need to monitor for flammability, and we need to monitor for changing conditions. So operational monitoring is once we've completed our recon monitoring, we've got our hazard zones set up, and now we're going to work. We have developed our defensive plan, and now we're putting it into action. We need to do monitoring throughout the operation for these 4 things. And the last thing, changing conditions. So maybe the product is in different areas. Maybe it's moved. Maybe it showed up in an area that we didn't detect it in earlier. Maybe there's a new product that we didn't know about. that's now leaking that wasn't before. And then also final monitoring. Once we've completed what we think we've completed our defensive activity, operational activity, we need to do a final monitoring to make sure that the work we've done has taken care of the issue. We want to make sure that our detection is accurate, and that's dependent on a few things. People using the monitors need to be trained in how to use the monitors. They don't need to be an expert or a laboratory expert, but they need to know how their monitor works. And as I mentioned before, they need to understand, well, the people using the monitor may not need to understand exactly the information that the monitor is reading, but whoever is analyzing that data and making decisions based on that data needs to understand what that monitor data means. Untrained personnel should not be using chemical detection monitors. We need to make sure we're using the appropriate monitoring equipment. Again, PID does not detect radiation. If we have a radioactive material, we don't want to be bringing out the PID. It's not going to do us any good. And we need to use the appropriate monitoring technique. What's that? Use the sign of the cross. We're going to move the monitor in a pattern that helps detect chemicals no matter where they are. So you're going to move it from high to low, left to right. That way we can cover the appropriate areas. Also, that animation was just an example. You really want to hold it in those positions for several seconds to get an accurate reading. You're not going to move it that fast. You move it that fast, you're going to miss something. Don't miss something. How can we best use our monitoring? Well, here's some strategies. Remember, the monitors that we use in emergency response are primarily life safety devices, not laboratory instruments. Emergency response is our primary mission. That means lives are in danger. That's the condition we are trying to resolve. They're not laboratory instruments that's going to detect things in the parts per million or parts per billion. And we are not laboratory technicians or scientists. We are emergency responders. We are trying to deal with issues that risk lives right now. Know the limitations of your device, like the PID. It's a very, very useful instrument. You just got to know how to use it. And also consider protecting instruments from contamination. If you're monitoring and a chemical splashes on it, now that monitor, even though it might be cleaned up, you got to decon it before you can use it again. And it may give you false readings. It's no longer useful. Make sure you're protecting your monitors. Your monitoring mission. So you're sent out to monitor. You need to know your mission. There's two general categories of mission. There's qualitative, means you're trying to figure out what is present. And there's quantitative, quantity, how much is present. You need to know which one of those missions you're going on. Also, what are the expected findings? If you're looking for methane and you start getting readings with the high levels of H2S, hydrogen sulfide, that's not what you're expecting. Also, you need to record your findings, record your readings. Now, the person using the monitor doesn't have to be the person with the piece of paper recording and the pencil recording your monitors. You can have a partner right next to you. You can also use a radio back to the entry team leader to your findings, and they can write it down. Much easier. We also need to perform periodic monitoring. That may be your mission. That's part of that operational monitoring. We do that to maintain the safety of our personnel in the work area. We need to check for changes in conditions. Some changes we're looking for. If we're doing work and it's supposed to be reducing the contamination of the atmosphere, we should be seeing that in our monitoring. If it's not changing or it's increasing, that's when we need to return from our plan implementation back to the planning stage of our problem solving method and come up with a new plan. Also, if you are doing a new operation, you're also going to monitor. So what are the things, information you're going to record? Your monitor findings, the ideal H conditions, your control zone location, and your periodic or operational monitoring results. Remember, numerous organizations have been cited or fined for a lack of documentation. If you're monitoring, you need to record your results. Also, know the alarm set points for each sensor. For example, these are just general levels, alarm set points. Your monitor may be different. For example, with oxygen, we have the high 23.5% or low 19.5%. LEL, as I mentioned before, it's going to alarm at 10% of the LEL or above. With carbon monoxide, it's normally 35 parts per million, could be 50, depending on your monitor. And then H2S, commonly, it's set at 5 parts per million. It could be also 2. All right, so when you're using monitors, what are some pitfalls that we could encounter? Not performing calibration or performing calibration wrongly. Not waiting for a warm-up period. Just brushing in there and your sensors aren't ready. You're going to get wrong readings. Poor monitoring technique. That's a sign of the cross. Moving too fast and not holding it where for moving too fast and not holding it for a time period for it to intake the air and get a good reading. Your environment is outside the temperature extremes, not allowing for sensor response time, that's moving it too quickly. Radio frequency interference, if the monitor is contaminated, not accounting for vapor density. So for example, propane, heavier than air. If you're holding the monitor up at your face or above your head, you're going to get less of a reading than you would if you held it at your feet. And not accounting for specific gravity. Remember, the specific gravity is where something's going to be stratified in water. If the material you're looking for has a specific gravity greater than 1, and which means it's going to be on the bottom of the water and you're sampling on the top of the water, you're not going to get accurate results. So you have to know your chemical and physical properties. All right, so that ends monitoring. Now we're going to move on to personal protective equipment. Many times you'll be wearing personal protective equipment while you're monitoring, especially in that recon monitoring. So let's get into PPE. So let's review, how do we protect ourselves from hazardous materials? Remember, time, we don't spend a lot of time in proximity to the hazardous material. Distance, stay away from it as far as you can and still get the job done. And then shielding. What is our shielding? PPE. PPE is our shielding. That increases the time we can spend in the hot zone where the material is, and it decreases the distance we have to spend away from it. When is PPE required? In general, when the atmosphere is known or suspected to be contaminated in the presence of a hazardous material, we're going to wear PPE. When vapors, gases, or particulates may be generated, or when direct contact with a skin-affecting substance may occur, we're going to wear PPE. Keep in mind, there are no universal chemical protective materials. There is no one material protects you from everything. There are some chemicals from which responders may not be able to protect themselves with PPE. So what are some things that we can, in general, expect to encounter and where we'd wear PPE? Solvents, corrosives, oils, flammables, dust, fumes, mists, and toxic fibers. What are some potential problems with PPE? There's degradation, permeation, and penetration. Let's talk about each one. Degradation. This is important. This is the physical destruction or decomposition of a clothing material due to exposure to a hazardous substance, usage causing breakdown of material, or environmental conditions, such as storing them in direct sunlight. Some visible signs of degradation is charring, shrinking, or dissolving. If your PPE starts dissolving, it's time to get out. Permeation. This is the process by which a hazardous substance moves through a given material at the molecular level. There are steps that go in this order for this to happen. The absorption of the hazardous substance into the outer surface material. Then it diffuses through the material, and desorption of the hazardous substance from the inner surface of the material towards the wearer, where it can be detected. So the chemical just moves slowly, hopefully slowly, through your PPE material. We can measure how fast that is, and we describe that as chemical breakthrough time. This is the time from initial chemical attack on the outside of the material until its desorption and detection inside of the suit. This is based on lab tests, so not real world. Breakthrough times are very important factors for suit selection. So you have to match up. The point of this is you have to match up the material of your PPE to the chemical. And each manufacturer has a chemical breakthrough time chart. Now, they don't test every chemical, but they test a lot of them. And they will tell you how many minutes it takes for that chemical to permeate through that suit material. Your best bet is you want it to be more than 8 hours. Or 480 minutes. Then there's penetration. This is the flow of a hazardous substance through parts of the suit, such as zippers, stitched seams, your face piece seal, pinholes, the exhalation valve, or suit fasteners. Excess of hot or cold temperatures may increase the chance for penetration. So penetration is different than permeation. Permeation happens at the molecular level. Penetration does not. Penetration is when there is an opening in the suit material and the chemical gets through. Selection criteria. In general, this is the things we need to know before we can pick our PPE. The hazard type and the measured concentration of the hazardous material. Also, the potential for exposure in the air, a splash of liquids, or other direct content. Situations that are unknown warrant the use of the highest level of protection available. So, if you do not know what material you're using, what chemical is present, and you don't know its measured concentration or the potential for exposure, you need to use the highest level of protection available. In general, level A suits provide the highest level of skin, respiratory, and eye protection. Level B provides the highest level of respiratory protection, just like level A, but a lesser level of skin protection. Level C is worn when the criteria for air purifying respirators are met. And level D for firefighters provides the highest level of thermal and respiratory protection. Now notice I said level D for firefighters. Level D is described or defined as the normal ensemble that you would wear for your job. We're firefighters, so this is our normal ensemble or group of PPE components. So what are the components of a level A suit? It is fully encapsulating, head to toe. It's a fully encapsulated chemical resistant suit. There's an SCBA, which is worn on the inside of the suit. It does have integral gloves. You'll also wear inner chemical resistant gloves as well, a hard hat, and boots. Selection criteria for level A. Any of these criteria may be met. They don't all have to be met. So any unknown atmosphere, you don't know what it is or how much it is, we're level A. Any unidentified atmosphere, any hazard that requires the highest level of skin and respiratory protection. Again, your science will determine that. Components of a level B include a chemical resistant one-piece suit. It does have openings usually at the wrists and the face. It also includes SCBA, which is worn on the outside. Also includes gloves, wearing 2 layers of chemical resistant gloves, a hard hat, and chemical resistant boots. Characteristics of a level B ensemble: does not afford the maximum skin protection, provides a reasonable degree of protection against splashes. So any of these criteria may be met for level B when the hazard and atmospheric concentration has been identified. A high level of respiratory protection is required. Less skin protection than a level A is required. And when concentrations are below skin toxicity thresholds. Level C components, it's going to be the same chemical protective suit or pretty close as a level B, except instead of an SCBA, you're wearing an air purifying respirator or an APR. You could also use a PAPR or PAPR which is a powered air purifying respirator. Chemical resistant coveralls, 2 layers of chemical resistant gloves, a hard hat, and boots. In order to choose level C, all of the following criteria must be met. Air concentration has been identified and are below the threshold limit value, and are within the canister's service limit. So you would put a chemical filtering canister, but they only will filter up to a certain concentration. The atmospheric contamination does not exceed IDLH at any time. The atmospheric contaminants, liquid splash, or other direct contact will not adversely affect unprotected body areas. The job function does not require an SCBA. And the atmospheric oxygen level is at normal level, 21% or 21.9%. Because you're not being supplied air like you are with an SCBA, you're breathing the atmospheric air, so it has to have the normal concentration of oxygen. Level C is distinguished from level B by the respiratory protection equipment. That's about the only difference. Unidentified ambient concentrations or organic vapors or gases require the use of level B protection. So if you cannot determine the concentration of the contaminants in the atmosphere, you need to wear level B so you have that supplied air. In emergency response, we don't wear level C all that often. Because many times we're dealing with unknowns. Level D components, bunker gear, and SCBA. When do we choose level D? When the primary harm or hazard is thermal. No other chemical protective suit provides the thermal protection as bunker gear and SCBA. There are flash protection level B and level A suits, but they are flash protection. Those are for accidental. That is not for entering a hazard that has a constant flame. Also, you can wear level D when there's no possibility of skin exposure, or there's a high probability of a viable rescue, even in an unknown atmosphere. You can wear level D when you have a high probability of a viable rescue, even in an unknown atmosphere. We just talked about in an unknown atmosphere, you wear level A because it provides the highest respiratory protection and the highest skin protection. However, it takes some time to put on level A. It also doesn't provide any thermal protection. As firefighters, fire-based hazmat response, we're going to have our level D, bunker gear, and SCBA ready to go. If time is of the essence, in order to save a life, we will risk not having the highest level of chemical protection by wearing our level D bunker gear and SCBA in order to effect a viable rescue. How do you know if it's a viable rescue? If they don't look like they're alive, they're not a viable rescue. Some potential problems with PPE: heat-related illness, such as heat rash, heat cramps, heat stress, and heat stroke. Heat can be a big factor with PPE, even if it's cold outside. The PPE, the chemical protective materials, are not good at regulating temperatures. So even in a cold exterior environment, heat-related problems are an issue. Keep that in mind. Heat stroke is an immediate treatment must happen in the event of heat stroke. Waiting for an ambulance may be too late. The victim's body temperature must be lowered, and you should treat for shock. This is immediately life-threatening. This is not an EMS class or a first aid class, so we're not going to get into heat stroke, signs, symptoms, or treatment. Just know that this is a possibility and action needs to be taken for the responder if they develop heat stroke. Some other potential problems wearing PPE, there's decreased agility and mobility. It's difficult to move around. You're wearing multiple layers of gloves. It's hard to grip things, tools and nuts and bolts, whatnot. Decreased vision, decreased hearing, decreased communication. Also, claustrophobia can be a problem. Your work mission as it relates to PPE must be determined prior to beginning operations. So before you go get your PPE on and go into the hot zone, you need to know what your goal is, what you're going to be doing. Also, a safe work rest period must be determined, and you base that on the anticipated work rate, the ambient temperature, the type of protective ensemble, which level you're wearing, and the responder's individual physiologic characteristics. So, are there some limitations on your work mission for the individual? One general category is air supply. So that's the physical condition of the responder. Is going to determine how much air, at what rate their air will be consumed, their workload, the level of SCBA training and experience, their anxiety level, and also heat stress. Also, as we mentioned before, the chemical breakthrough time will limit your work mission time. These are again found in suit manufacturer compatibility charts. Remember, chemical breakthrough time deals with permeation at the molecular level. There's also other physiological factors, such as poor physical condition and obesity, alcohol and drug use. This includes your normal prescription medications, could affect your work mission or your ability to perform your work mission. Dehydration and sunburn, your age, whether or not you have an infection, illness, or other disease could limit your work mission. And then the environmental factors, elevated temperatures. Just because it's cold outside, you might be working in an area of an industry next to a furnace and be dealing with elevated temperatures even though it's cool otherwise. Also, you're dealing with burdensome PPE. You're wearing a lot of it and it doesn't breathe very well. And then also sensory overload. Your vision may be obscured, your hearing, there could be, you could be working in a very noisy environment, and all that can contribute to limiting how long you can work. Workload factors, your work may be physically demanding, moving and lifting and all that, putting on whatever work, digging. The distance from the dress out area, so you get dressed in one area and have to walk a long way, or hopefully ride in a ATV or something. And also the urgency of how quickly we need to get this mission completed. When we are dealing with personal protective equipment, it needs to be inspected. This is our shielding from a chemical. So when do we need to inspect it? We need to know these 5 situations in which we inspect it. When we receive it new from the distributor, so we get it delivered to our agency, we need to make sure it's in good order. We're also going to inspect it when it's selected for entry operation. So before we get in the suit and go in the hot zone, the hazard zone, we need to make sure it's in good order. You need to inspect it prior to performing maintenance. Some types of suits, like level A suits, they have maintenance that need to be performed. So we're going to inspect them before performing that maintenance. Periodically during storage, per the manufacturer's recommendation. Also, when questions arise concerning problems. So if we get notification that another hazmat agency has had an issue with their suit, we're going to check out our suits as well, perform an inspection. So what's part of that inspection process? We're going to confirm chemical compatibility before we go into the hazard zone. We're going to visually inspect for any imperfections, such as separated seams, tears, malfunctioning Velcro or zippers, non-uniform coatings, or shelf deterioration, such as cracks. We're also going to hold it up to light to check for holes, see if any light shines through the material. Sometimes while we're wearing PPE, an emergency can arise. We mentioned heat stress earlier, but there are some other things as well. Our suit can experience degradation. That would be an emergency. If you start to perceive odors, or you feel skin irritation, or if you notice an unexpected color change of the suit, or you start feeling some type of other discomfort that you weren't expecting. If you have an increased resistance to breathe or difficulty breathing, increased fatigue, unusually, visual or communication interference. So if you can't see what you're doing or where you're going, or you're not able to communicate through your primary communication method, that would be an emergency. If for some reason your movement is restricted unexpectedly, or if you start having signs or symptoms of illness, nausea, rapid pulse, chest pain, or other. If any of these conditions occur that warrant a PPE, that describe a PPE emergency, call for the IC notification and report to emergency decon. Two things happen in a PPE emergency. You're going to notify the IC and you're going to report to emergency decon. There are some standard hand signals that we use in the event that our radio communications are inoperable. One hand across the chest indicates I'm low on air. Two arms across your chest in a cross means I'm out of air. Another typo. The one on the left with the two thumbs up means I'm okay. And I forgot to change that one too. And arms up in the air, waving, both arms up means emergency, get me out of here. I apologize for those mistakes. I will fix that. So thumbs up means I'm okay, we're all good. And then arms up in the air, waving means get me out of here, I have an emergency. Some general safe practices with all PPE: avoid abrasions. So as you're walking, and if you're in a tight space, you want to try to avoid rubbing your suit on surfaces. Wear 2 pairs of gloves, work in pairs, use the buddy system. Avoid contamination. If you don't have to get in a chemical, don't get in the chemical, and avoid kneeling. That's like the one thing not to do. Don't kneel down in your chemical protective suit, because that's just going to cause abrasions, and you're probably going to be kneeling in the material anyway. Bad idea. Don't do it. Don't kneel. All right, so that's chemical monitoring and personal protective equipment.